So, in this case, we're dealing with a circle. So, the area of a circle, what is it? We all know it and love it. Pi r squared. Not to be confused with the circumference of a circle, which is 2 pi r, but easily confused with the circumference of a circle because they are so similar. Area of a circle is pi r squared. So, what I had the students do last year, and this seemed to really help us kind of understand what can be plugged in before we take the derivative, what can be plugged in after. We want to identify the variables from the equations and determine if the quantities are constant or changing. Determine the variable that you, and also to determine the variable that you will be solving for, right? So, you can start off with looking at the variables that you see in your equation. We have 2 variables in this equation. What are those variables? R and A, right? R stands for radius, A stands for area. In this context, when the oil is spilling out, are those variables changing or constant? Is the area always a certain amount? Is the radius always a certain amount? No, as I poured water on the floor, both the radius and the area of that circle were changing, right? So, both of those are changing there. So, for variables that are changing, we got A, which is our area, and R, which is our radius. Now, sometimes some of your variables are not changing, like the radar gun problem that we looked at. The police car was 30 feet from the road, and it wasn't moving. So, in that case, that distance was constant, right? And it would be the quantity that's not changing. We also are going to be talking about the rates of change, right? So, we do have one thing that is going to be constant. Okay? Because it tells us, suppose that the area of the spill is increasing at a constant rate of 4 centimeters per second. So, the area is increasing at a rate of 4 centimeters squared per second. What, would be the representation of that? What would I call that in the equation when I take the derivative? What? A prime, I generally like to use dA dt instead. So that's what you're going to probably see me use most often. It is acceptable to use A prime. So you can use that if you would like as well. When I just find it a little bit more helpful because it relates to dy dx better, and when we get to differential equations, which we haven't done yet, that notation carries over to those a little bit better too. So I usually stick with dA dt, but A prime is acceptable and could be used. So that is the rate area changes. And we know it's constant. We know that it equals 4 centimeters squared per second. Right, we don't have to find it. And then we need to think about what we're finding. What is the question asking us for? The rate at which the radius is increasing. What's that going to be represented with, like in the equation? It's going to be dr dt, rate radius changes. And let's go ahead and think about units for that. how do you measure a radius? We measure it in length. In particular, for this case, what unit are they using for length? Centimeters. So this is going to be centimeters per second are going to be our units for our answer, because we measure radius in centimeters, and then time that we're using here is seconds for this. Notice, like, area is square centimeters, because we measure area in square units, but radius would just be measured in centimeters. So we'll do that. Now, you don't always have to write all of this out with what it means written out beside of it. I am just doing that for our benefit because these problems are new. So I have, it won't let me copy in color for you. They don't give me that power because they did mess up a while back and they accidentally gave us access to color copies. And I was making color copies of everything, but I didn't even know it. Like, if anything was in color, like, it was just set to default. Like, if there was an email address that was underlined in blue, that counted as a color copy. If there was a link that got, like, I could have everything in black and white on the page, except for that little bit, and it was counting, like, as our color copies, and we get charged a lot more for color copies than we do for black and white, and so they don't give us that power anymore. But I've got it in red up here because these two steps don't apply to this situation. All right, so plug it. If we had any constants that we could plug into the equation, if A or R were constant, we would plug those in right now. However, they are not, and I have a constant, but it's dAdt. I can't plug it in right now because I don't have a dAdt. Right? I'm going to have to take the derivative first before I can plug that in. And then you're going to convert the equation to one variable if necessary. But my equation is, I guess technically that's two variables because it's A equals. What I mean is one variable on each side, right? So A equals pi r squared. I only have one variable there, r, right? So I don't need to do that in this problem either. So that makes this a little bit of an easier problem for us to start out with. And we'll see some examples where we have to do these things here in a minute. So when I get to this point, I want to take the derivative of the equation with respect to time. Okay? So A equals pi r squared. I'm taking the derivative with respect to time. Remember, pi is just a constant. So this is just a power rule problem. So the derivative of A is going to be dA dt. And for pi r squared, I will get 2 pi r. What do I need with that? dr dt. We can't forget that because when we're taking the derivative with respect to a different variable, everything we take the derivative of needs a d whatever dt with it. Okay? So here's our derivative. Looks beautiful. I do find it interesting that the derivative of area is circumference for a circle. I do not know if there's like a reason. Anyway, we don't have time to explore that right now. We're not going to worry about it. So then we are going to plug in all given values from step 2. Right? So I know dA dt is 4 square centimeters per second. So I'm going to plug in 4 for my dA dt. And then I've got 2 pi, and r is not a constant value that we're given, but they do ask us in the question. I should have put this over here in my find, because I'm supposed to find dr dt when radius is 50 centimeters, right? So I'm finding this when r equals 50 centimeters. So I probably should have written that down earlier. So I'm plugging in 50 for my r, and then I do not plug in anything for dr dt because that's what I'm looking for. Right? So I am just going to solve now. So I've got 4 equals 100 pi dr dt. we'll divide by 100 pi. And when I do that, I get, so that'll reduce to 1 over 25 pi equals dr dt. So 1 over 25 pi, this is the rate of change of the radius with respect to time. So that a radius is measured in centimeters, time is measured in seconds. So it's going to be 1 over 25 pi centimeters per second. Or, where's my calculator? Let's just get this would probably be a calculator inactive problem, and that'd be the answer that they would be looking for. But just for our, curiosity here, let's see what that is as a decimal. It's like 0.01272 centimeters per second. So when you're out to 50 centimeters, right, which is going to be a pretty good size circle, the radius is really not changing all that quickly, right? If we looked at it whenever the radius was only like 1, right, the rate of change would be much higher for that. Okay, questions? So if you are worried about your oil spill reaching the beaver dam or wherever it's at, you're going at a rate of 0.01 centimeters per second at this point. That is only going to just keep slowing down. When we learn some more stuff, you could probably use that information to be able to tell how long it's going to take. Now, you can't exactly just use this number because the rates, we could take this number and see how long it would take to hit the beaver dam. But it would be even more time than that because this rate is going to keep getting slower and slower and slower and slower as the circle expands there. Okay, questions? All right, so we're at on time. Okay, this is almost the same problem. Textbooks love to put this problem in there. I like the oil spill problem better because I feel like I'm seeing, even though maybe it's oversimplified, I'm seeing where it could be used. I feel like, while this is a actual application, that nobody cares about dropping pebbles in ponds and seeing how fast the ripple goes out. Although, once again, we're oversimplifying it here. A pebble in a pond, nobody cares. But an earthquake in the ocean that causes a tidal wave that's expanding, people do care about that, right? However, that scenario is going to have a lot more factors that complicate it, such as the shape of the ocean floor and different things that could come into play there. I'm sure more things that I don't know about, but we could think of it, we could take this general idea and apply it in a bigger concept there. So you got a pebble is dropped into a calm pond using ripples, causing ripples in the form of concentric circles, as shown. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. So we have a different scenario here. We are not pouring water on the floor at a constant rate this time. The radius is increasing at a constant rate. Okay? So as the radius increases, the area is going to increase. But will that area increase at a constant rate also? It will not, right? If we have a little tiny circle, it has a very small area. Well, if we double that, if we increase that radius by 2, now we got a pretty good size circle, right? If we increase that radius by 2, the area is increasing at an increasing rate, right? It's going to get faster and faster and faster in this case. So when the radius is 4 feet, at what rate is the total area of the disturbed water changing, right? So we are looking at circles again. our area equals pi r squared is going to be the formula that we're working with. I want you guys to try this because this is basically the same as the last problem, although we have some different pieces of information. So I'm going to freeze my screen to go through this, and I want you guys to try it on your own. Like the scenario where I'm pouring water, but it's a little bit different. But the radius and the area change both, right? You can't, they have to. You can't change the radius of the circle without the area also changing, right? Like if one is constant, the other has to be constant as well. So they're both, A and R are both changing. The dr dt is constant. Okay, they tell us that in the problem. They say the radius of the outer ripple is increasing at a constant rate. So the radius is increasing, that is dr dt. Whereas last time it was the a dt, right, that we had as constant. And then it says, when the radius is 4 feet, at what rate is the total area? So the rate area is changing, is the a dt, that's what we're finding. And I like to put when r equals 4 right here with it, because while we cannot plug 4 in before we take the derivative, because 4, like the radius is changing, we are looking specifically at dA dt at this point where r equals 4 for that. And so on this problem, you do not have any constants to plug in. You do not have to convert the equation to one variable if necessary for these problems. So the derivative is the exact same as it was on the last problem. It is just a power rule problem. It does not change how you take the derivative at all here. What does change is where you plug the numbers in at. So this time we're looking for dA dt. We're trying to find dA dt. So we are not going to replace dA dt. It stays there. We've got our radius is 4 at the point that we're concerned with, and our dr dt is 1. So whenever you multiply that together, you are going to get 8 pi. I on purpose left the units off because I'm interested to see what you guys have as your units. What would the units of our answer be? What do you think, Jericho? Feet per second is what I saw mostly. It is also not correct. Yes, because this is dA dt. So think about, this is another reason that I like to call it dA dt instead of A prime, right? So we're doing the change in A over the change in T. A stands for area. How do you measure area? Square units, right? So you measure area in square feet, right? If I ask you for the area of this room, you can't tell me 70 feet, right? That would be a silly answer. Well, 70 is too small, first off. But, you know, you can't tell me 400 feet. It is square feet. Each one of these little tiles is a square foot, right? And then dt is time, right? So this is going to be square feet per time. In this particular case, we're measuring time in seconds. So seconds goes in the bottom. There. All right, questions? All right, let's do a different one. Let me check my closet here. Let's see if I have. I've got the balloon pump up here with the prom stuff, but I don't think I have any balloons. So I'm not able to demonstrate this. Imagine in your mind, hopefully everybody has blown a balloon up before, seen a balloon blown up, right? So if you were on prom committee last year, we saw a lot of them blown up. So whenever you blow up a balloon, okay, a balloon, if you give it like one breath, right, it's going to blow up a little bit. And then give it another breath. It's going to get bigger. And then another one, a little bit bigger. But towards the end, think about like if you were trying to blow up a balloon until it pops, right? Then each breath, are you making a lot of progress there at the end? Like it gets bigger, but it's not getting bigger. Like it's not like you have a radius of 1 inch, and then 2 inches, and then 3 inches, and 4 inches, 5, 6, 7, 8, right? Those last breaths are just stretching that balloon a little teensy bit more because it's taking a lot of volume to increase that radius, right? So this is similar to the pouring the water on the floor, right? Each amount of air that you blow in, so like if each breath is about the same, you could think of breaths. Or like if you have a balloon pump, which I have in the I have over here in the closet, but I don't have any balloons. I should have planned ahead. Like that's blowing air in at a constant rate, right? So describe how the length of the radius of the balloon changes as the air is pumped into the balloon. So this first part's just asking us to think about it. So as air is pumped into the balloon, the radius. So as you blow the balloon up, does the radius increase or decrease? Definitely increases, right? No doubt about that. The radius only increases. So the radius increases at a, is it going to increase at an increasing rate or increase at a decreasing rate? At a decreasing rate. Because if we think of like graphing this, if we're graphing this, the radius starts off at 0. It's going to jump up quickly at first, but then more slowly as we go on, right? So, part B says find the rate of change of the radius when the radius is 2 inches. So that's the part where we got to go through our steps and actually solve. A is just asking us to think about the scenario. There's a chance you get a multiple choice question where it tells you all this and doesn't want you to solve the problem. You just have to tell the radius is increasing at a decreasing rate for that. Because that is like a calculus idea as well, right? So we're going to write the volume, the equation for the area or the volume of the shape. In this case, we're dealing with volume. Anybody remember volume of a sphere? It's not 1/3. 1/3 is like a cone. It does have fraction in it, though. Not 1/4. It's 4/3 pi r cubed. Most of the time, if they give you a volume of a sphere problem, they put the formula in the problem. So, but it would be in your best interest to also have that memorized. Yes. Area of a circle, you for sure have to know they are not going to give you that one. So area of a circle, circumference, they're not going to give you that. They're definitely not giving you things like most 2D figures, they're not going to give you the volume or the area formula for. So even something, you probably won't see trapezoid on related rate problems, but we'll see them in a different context, like trapezoid, rectangles, triangles, circles. 2D figures we need to know, pretty much. Most 3D figures, they're going to give you the formula. Maybe not a rectangular prism because that is just length times width times height. Most of the other ones, they're going to give you the formula in the problem for that. Although it never hurts to have them memorized as well, just in case. They're mean on the Math 3 exam. Like they don't give you volume of, like there was one. They don't give you a volume of a sphere. It's a sphere problem. It's not even that hard of a problem. They didn't give them the formula. So you can rest assured that I had several not get it because they didn't have it memorized. I wish they'd give you the formulas on everything because, 20 years from now, you may not remember, well, we may not remember how to do any of this 20 years from now, but we might have an idea, but you need to know where to start from. You got to have formulas. So, all right, but we're going to identify our constants and our changing. So changing is the volume changing? Yes. Is the radius changing? Yes. Those two have to go together. If the radius changes, the volume has to change in a sphere for that. For constant, none of our variables are constant, but I do believe we have a rate that is constant. Air is being pumped into a spherical balloon at a rate of 4.3 cubic centimeters per minute. Is that the VDT or the RDT? It doesn't specifically say, but it's V because it's the volume of air. I can know that because it's cubic inches per minute, right? So, and you just about would have to say radius to be talking about the radius here. But volume, you don't necessarily have to say the word volume to mean volume here. So dV dt is 4.5 cubic inches per minute. And then we need to think about what we need to find. And it says, find the rate of change of the radius. What is that? Rate of change of radius is dr dt when r equals 2. Okay? And it doesn't hurt right here to go ahead and think about units. What's radius measured in? Inches. What's our time measured in? Minutes. So we're looking at inches per minute should be our units on our answer. Okay. Much like the last two, you do not have to plug in any constants. You do not have to convert the equation to one variable. Those things are not necessary for this problem. We're going to take the derivative. It looks a little complicated, but it's really not. 4/3 pi is just a constant, right? So you could even do it this way. You got dv dt equals, you could leave the 4/3 pi right here and then just do 3r squared like that. This is over 1, this is over 1. The 3 right here can cancel the 3 right here. And so we get 4 pi r. Oh, wait, hold on. I should not do what I'm doing. I'm being reckless. Because what have I forgotten? dr dt. And then let me go over here and do 4 pi r squared dr dt. Interesting fact, 4 pi r squared is the surface area of the sphere. And I wonder if that's related, like the derivative of area is circumference for a circle. The derivative of volume is surface area. I feel like it's got to be related, but I just feel like I don't understand that well enough about like why. But anyway, not necessary for you to know that though. We need to plug in all values from step 2. So we are trying to find dRdt. It will not be replaced. Everything else should get replaced. So we've got dV dt is 4.5. We got 4 pi. Our radius is 2. And the rdt is not going to be replaced. So 2 squared is 4. 4 times 4 will give you 16. So we got 4.5 equals 16 pi dr dt. We will need to divide by 16 pi. And so, dr dt equals 4.5 over 16 pi. If you find yourself doing this and getting a number like this on a calculator inactive question, stop. You don't have to simplify, right? Let's see what it is with decimal. It's 0.089525. And we said the units for this, we're talking about radius, which is measured in, oh gosh, what was it? Inches, and time, which is measured in minutes. Oh gosh, not good enough. Okay, questions? Alright, so, gosh, I should have got through those. As much as I'd love to do this, we don't have time because this one's harder. So, that'll adjust your homework quite a bit. So, tonight, let me look at these and I'll tell you which ones you can do based on what we've done. We're on 194 and 14. 14 you can do. I want you to try 15. We didn't do a cube. We've only done circle context, but a cube is a pretty simple thing to start with. So I think you might can. I think 14 and 15 we're going to be okay. 14, 15. I'm not going to do 16 because the surface area we haven't talked about. The cone we definitely can't do. Let's see, about 44. Let's try 44. It's an equilateral triangle, but they give you the formula, so I think that makes it a lot easier of a problem. And we can do 46, or should be able to do 46. There. So, 14, 15, 44, 46 are the only ones we're going to be able to do since we only got half the notes. I lived my life just trying to catch up.